Forgot to start the camera, but we can start from now. We didn't miss anything because what I said so far is reported in the last lecture. So again, Ct is the max storage into the catchment. Remember that we neglected evapotranspiration so far, and therefore Ct is nothing else than rainfall from the beginning, from time 0. So Ct is max storage into the catchment at time t. Wt is average storage, is storage, just storage. It's an average over the catchment. Okay, so I now want to invert this relationship. Before inverting, let me emphasize one thing. We could, from here, estimate the value of the max storage into the catchment. In order to get the max storage, we have to equate Ct with the Cmax. Cmax is the upper value of storage in the individual location where the max of water can be stored. Wt is the max storage over the catchment. Remember, when I talk about Ct, I talk about an individual location. When I talk about Cmax, is I look into the catchment. Into the catchment, there is one point where the storage is highest, and the storage in the highest point is Cmax. When I look at the whole storage, there is a maximum amount of overall storage that I can compute. So keep in mind the difference between an individual location and a global view over the catchment. So let's suppose that I equate Ct with Cmax, and then I can say that Wmax is equal to Cmax divided beta k plus 1, and that's it, because when Ct is identical to Cmax, we have 0 inside here. 0 to any exponent is just 0, and therefore here only 1 remains. So max storage over the catchment is equal to Cmax divided beta k plus 1. Remember that beta k is always greater than 0, and therefore you see that, or it can assume a limiting value, a limiting lower value of 0. So you see that the average storage over the catchment is always lower, or in extreme condition the same with respect to the max storage in the individual locations. And this is what we expect, because if Cmax is the max storage in a point, the max storage over the catchment is certainly lower than that. Okay. Now, as I said, let's keep this relationship written somewhere, and I need to delete it because I don't have space on the blackboard. And then let's make a very simple analytical exercise in order to get an explicit representation for Ct. And in order to do that, what I have to do is just to manipulate this expression. Let me now make the first step by writing that Wt divided Cmax multiplied by beta k plus 1 is equal to 1 minus Ct divided Cmax to the power of beta k plus 1. This is just the first step, where I took this multiplier and I brought it on the left-hand side. Okay, the next step is to take this 1 and bring it on the left hand side. So this is very simple. I'm just rewriting. Let me, when I do this, let me change the sign left and right, okay? Because otherwise I keep a minus here, which is disturbing, at least to an engineer. So let me write 1 minus Wt divided Cmax, which multiplies beta k plus 1. Change the sign. This is equal to 1 minus Ct divided Cmax to the power of beta k plus 1. And now I have to remove this exponent in order, if I want to get an explicit representation for Ct, I need to remove this exponent by elevating both members to the exponent 1 divided by beta k plus 1. So let me delete above here. And let me write it as follows. 1 minus Wt divided Cmax times beta k plus 1. Let me elevate it to the power 1 divided by beta k plus 1. And this is equal to 1 minus Ct divided Cmax. And we are almost there, as you can see. Let me delete here. We can write Ct is equal to Cmax, which multiplies 1 minus Wt divided Cmax beta k plus 1 to the power of 1 divided beta k plus 1. If I didn't make any mistake, this should be what we are looking for. And there is the expression written here. So let's compare. You see, Ct, it's equal to Cmax. Yeah, 1 minus 1. Yeah, it's fine. It's written in a slightly different way, but it's fine. Okay, so let's keep also this relationship written somewhere. And then the next question is how I can apply this model. First of all, we need to introduce a couple of more concepts related to this model. First, we need to introduce evapotranspiration. Just 1 second, yeah. I need to go to my web page because there is something that I would like to show you from there. Okay, let me follow the workflow that is described here. So you have now two expressions available, which are Wt as a function of Ct, and the other one, Ct, as a function of Wt. Okay, so remember what is Ct. We neglected evapotranspiration so far, so that it's rainfall from the beginning of, from time zero, let's say. I was saying from the beginning of a given event, of a given rainfall event. Let's say that it's a rainfall from time zero. So basically, at a given time step t, you know Ct, because you have observations of rainfall. Usually the model is operated at discrete time steps, which the time step, usually it's the same as the time step of the observed data. So you may have daily rainfall data, which means that you obtain from daily rainfall data, you aim to obtain daily river flow data, and then you operate the model at daily time step. If you have hourly rainfall data, you may run the model at hourly time step, because what is important? It's important that if you decide a time step like hourly, at each hour you need the input information. If you don't have the input information each hour, in principle you cannot run the model at hourly time step. If you have your information at daily time step, you need to run the model at daily time step. The literature proposes also techniques for, they say, disaggregate input data, meaning that if you have daily, you can disaggregate them to the hourly time scale. But this is quite complicated and very uncertain. What we do in the practical engineering design usually is to run the model at the same time step as observations. Okay, so in any case, given that you have the observations, you at each time have an estimate of Ct. And therefore, as time passes from Ct, you pass to Ct plus 1. Okay, but we have to take into account that Ct cannot exceed Cmax. So we have to establish a condition, a constraint. And the constraint is that Ct is lower or equal than Cmax. What happens if it rains so much that Ct plus 1 becomes higher than Cmax? What happens is that the catchment gets saturated, and whatever it rains above Cmax doesn't infiltrate, it's not stored, and it's immediately transformed in surface runoff, which means, at the end of the story, river flow. So again, I have my rainfall data that allow me to compute the progress of Ct, from Ct to Ct plus 1, Ct plus 2, and etc. This is what is written there. If I realize that Ct becomes higher than Cmax, then, so I need to write a condition. If Ct is higher than Cmax, then Ct minus Cmax goes to runoff, and Ct is equal to Cmax. So my algorithm should establish this condition. If storage Ct becomes higher than Cmax, this is not possible by definition, because it cannot be in any point of the catchment stored more water than the max possible storage, and therefore I have to do two things. First, tell the PC that the amount of Ct that exceeds Cmax, Ct minus Cmax, is transformed in runoff. And second condition, Ct is equated to Cmax, because it cannot be higher. Okay. And therefore, in order to translate in computing terms, in computer language, this condition, let me expand, increase the size, just 1 second. The best possible way is that one computes a first contribution to surface runoff, which is called here ER1, which is equal to max Ct plus Pt minus Cmax. You see that Ct plus Pt is equal to Ct plus 1. From Ct, I sum the rainfall at current time and I get to Ct plus 1. I subtract Cmax, like I do there, and then I compute this first contribution to the surface runoff. Why do I introduce this condition max between this difference and 0? Because I don't want that a contribution to surface runoff becomes, for whatever reason, negative. Okay? So, if indeed Ct plus Pt minus Cmax is greater than 0, I take it as first contribution to the surface runoff. If it is still lower than 0, because Cmax is greater than Ct plus precipitation, then I take as first contribution to surface runoff 0. This is the algorithm, which says basically the same thing that I wrote there, but this is in computer language. And this is the first contribution, which is activated if and only if Ct becomes greater than Cmax. Okay. But I can have, even if Ct is lower than Cmax, I may have anyway a contribution to runoff, which may come from the locations in the catchment that get saturated. So even if Ct is lower than Cmax, I may have nevertheless some location in the catchment that are saturated, because remember that Cmax is the max potential storage into the catchment. But there are locations that have a lower storage, like impervious ones. And therefore, whatever rains over impervious, impermeable locations, it's transformed in runoff. I have to take into account this. And this happens even if Ct is lower than Cmax. This happens even if the basin is not completely saturated. Remember that Ct greater than Cmax means that the basin, the catchment, is completely saturated everywhere. But even if it's not, there are locations where it is saturated, for instance, in previous locations. And therefore, I have to compute the contribution to runoff from these locations. How do I compute it? Let me define a second contribution then to surface runoff, which I call ER2, which is equal to, let me use the same symbols, Ct plus 1 minus Ct, and this is basically the rainfall that is fallen from T to T plus 1, so for the rainfall that is fallen in the considered time step, minus, let me open a parenthesis, Wt plus 1 minus Wt. Basically, I am subtracting from rainfall the amount of water that is stored at the given time step. Same symbols here. And then if you sum ER1 plus ER2, you have it's the contribution to surface runoff which eventually is river flow at time t. Good. Good. Okay, now an additional concept introduced by the model. So you compute this year 1 plus year 2. What is the sum? It's the sum of the water that comes from several locations into the catchment. So the water may come from here, from here, from here, and from here, and from here. This water is surface runoff produced in a distributed fashion over the catchment, and then this water has to go to the river. If the catchment is completely saturated, because we got to a city that is higher than Cmax, water is produced everywhere, but still has to travel to reach the river. So we need to take into account this travel time. And the model then does it by introducing a conceptual scheme. And at this stage I can go to my presentation. Basically, you have here year 1 and year 2. They are summed. And then there is a conceptual scheme that simulates the travel of each drop of water to the river and to the closure. The closure is the river cross-section that you find here. And in order to simulate this process, the model assumes that surface runoff is split into parts by introducing an additional parameter alpha, which is varying, it's a weight, is varying from 0 to 1. So basically, through alpha, you split the surface runoff in two components, and if alpha is 0.5, it's split in two equal parts, and one contribution is routed through a linear reservoir, which you know already. So the inflow to the linear reservoir is alpha times year 1 plus year 2, and then the outcome from the linear reservoir is considered to be flow to the closure, river flow at the closure. The other component of surface runoff is routed through a sequence of 3 linear reservoirs. You remember that the linear reservoir has a parameter, which is the constant k, it's a time. So basically, in applying this conceptual scheme, I am introducing one more parameter to the model, which is alpha, one more, which is the constant k, called here ks, of the single linear reservoir, and one more, that is the constant k, called here kq, of the 3 linear reservoirs. They are assumed to have the same identical time parameter kq. You may wonder why the surface runoff is split in these two components. Because one of them represents a fast travel, a fast trip to the closure, like the one that may take place over the surface, water flowing on the top of hill slopes. The other component is a slow response like the trip that the water drops may take by infiltrating into the catchment and flowing in the underground. So there are two possible trips from each individual location of the catchment to the closure. One fast way and one slow way. At this stage, I am sure that you believe that the model is extremely complicated. Actually, it's not. We will apply this model, and I will show you that the code, the R code, for applying this model is made by a few instructions, because everything is extremely easy to apply. You have analytical relationships for CT and WT. CT is known because it's rainfall over the catchment. So you may compute WT from it. So you have both CT and WT known. If you remember how year 1 and year 2 are computed, once that Cmax is defined, it's very easy to compute year 1 and year 2. Year 2, it's written here. Year 1, it's in the previous slide. You see, you know CT. CT plus 1, you know CT, you know WT plus 1 that can be computed from CT plus 1 with the analytical relationship that you have, and you know WT, same thing, can be computed by CT. So computing this, it's just a difference, nothing else. Once that you know the parameters and the input data. The same for year 1. Year 1, you know Cmax, you know CT, very easy to compute. And therefore, year 1 plus year 2 are very easy to compute again. Applying alpha, it's just a way to split the sum year 1 plus year 2 into components. And for applying the linear reservoir, there is a very simple analytical relationship to be applied at each time step that gives to you the outcome depending on the input. And also the sequence of 3 linear reservoirs, it's a very simple relationship. Those of you who already took a background in hydrology know that this is nothing else than what is called the Nash model. Very simple analytical relationship to apply it. So it is just a sequence of very simple instructions and a code that is less than 1 page long. We will see it. There is one last thing that I didn't deal with so far, which is accounting for evapotranspiration. Now let me say something about it, because again it's very simple, but we need to discuss a little bit. Because in this subject, we don't discuss in detail about evapotranspiration, but of course we need to know what is, and there are links in my web pages to it, and there are a few things that I would like to point out. First of all, evapotranspiration depends on several things. It depends on rainfall, it depends on soil saturation, it depends on wind and temperature. The process governing evapotranspiration, it's known. Evapotranspiration, remember, that is composed by evaporation from liquid surfaces and transpiration from plants. So you know how evaporation works. It's a physically based process, and not only physics, there is also something related to temperature. But it's basically it's a process that we know in detail. Even transpiration from plants, it's a process that is difficult to describe because there are several external forcings on it, but it's something that it's a physical and ecological process, so we know everything about it. But these processes, even if we know how they work, they are difficult to describe because, in analytical terms, because of the complexity of their complexity and their sometimes chaotic behavior. Chaotic means that if you make a small change in the initial and boundary condition, the results completely change. And therefore, evapotranspiration is usually described by using empirical relationships. Empirical relationships that have different level of complexity depending on the input data that you have. So if you look for evapotranspiration in Google, you will find several empirical relationships. Some of them are complicated, some others are simpler. Evapotranspiration. And transpiration. Yeah. And to give you an example, in some cases, wind is highly effective on evapotranspiration, but in some cases we don't have wind data, and therefore we have to use an empirical formula for estimating evapotranspiration that doesn't take into account wind, because we don't have wind data. If we have wind data, we can use a more detailed formula. So there are several formulations, as I said, which give to you estimation of evapotranspiration with respect to a reference situation. The reference situation is the situation where there is unlimited water available to plants. Because of course, if you have no water available for plants and no water available for evaporation, your evapotranspiration is zero. Plants cannot transpire because they don't have any water to get with the roots. And water cannot evaporate from liquid surfaces because there are no liquid surfaces. The opposite situation is when you have plenty of water. You have abundant water, and therefore, of course, plants transpire at their maximum potential, and evaporation is at its maximum potential. This reference evapotranspiration is called potential evapotranspiration. I don't remember, sorry, I have a gap in my memory. Evapotranspiration, yeah, I didn't remember how it was written. Okay, this is potential. Why potential? Because it's the maximum. And this is usually called EP, which depends on time. And this is usually expressed as rainfall with a length, with the unit of a length. So it's a volume of water that is evapotranspirated per unit area, potential. And then there is actual evapotranspiration, or simply evapotranspiration. Actual, which is called ET usually. So you can, of course, easily understand, you can easily get that actual evapotranspiration is lower or, in limiting condition, equal to potential evapotranspiration. So ET is less or equal than EPT. EPT, as I said, is estimated through empirical relationships, and you can find many on the web. We will assume in our treatment, in our course, that EP is given in some way. We take it as an input variable. And then Heimold assumes that actual evapotranspiration ET is equivalent to EPT for CT equal to Cmax, which means that when the catchment is saturated, one may equivalently say Wt is equal to Wmax. When the catchment is saturated, actual evapotranspiration is equivalent to potential evapotranspiration. And also, IMOD assumes that ET is equal to 0 for Wt equal to 0, which is equivalently can be written as Ct equals 0. And then there is a linear relationship in between, so it's something like that. One may use Wt as the independent variable, and then it varies from 0 to Wmax. And then ET as the dependent variable varies from 0 to EPT. And then there is a linear relationship connecting the two. This is an assumption made by IMOD. Okay, good. How to write it in mathematical terms through this relationship here? So